Welcome to the Deep Dive, the place where we tackle these really intimidating fields of research, stack up the sources, and then try to pull out the knowledge you need to be genuinely well-informed.
Today, we are getting into one of the most exciting and I think strategically important areas of AI.
Reinforcement learning,
Hmm,
or RL.
exactly. This is the whole paradigm where machines learn strategies, but not by being shown the answer.
Yeah.
They teach themselves. It's all trial and error, a lot like how we learn complex things.
Right, and our source material for this deep dive is all about the fundamentals and, more importantly, its industrial applications. So our mission, I think, is pretty clear.
Yeah, we need to figure out why RL is so critical right now.
And how it's really fundamentally different from standard machine
Right.
learning. Then we need to get into the core algorithms that, actually make this all work.
I think we have to start with the core promise of RL, which is its relentless focus on long-term strategy, on sequential decision-making.
Okay.
That's really the biggest distinction we need to unpack first.
Let's do it. So that if you're using standard, say, supervised machine learning, you're really aiming for a one-shot decision.
Right.
It's great for flagging one email as spam or recognizing an object in a picture, but as soon as that decision is made, that's it. The process is over.
Exactly. And RL is it's a different beast. It's not solving a single prediction problem. It's solving a control problem
Hmm.
over time.
A control problem.
Yeah. I
Well,
mean, imagine a standard ML model. It's trained to maximize clicks on a news site.
okay.
It sees some sensationalist clickbait, it predicts a high click-through rate, and boom, it recommends it. That's a short-term win.
But the business goal isn't just clicks right now. It's about keeping users around. It's engagement and retention later on.
Precisely. The RL agent, it takes a long view. It understands that, yeah, recommending low-quality clickbait gives you that immediate reward, the click, but it leads to a really negative long-term outcome. User churn, reduced engagement, all of it.
Mhm.
So RL is designed to optimize for these big, sustained goals like long-term profit or the number of active users. Not just some technical metric like accuracy. It's built for strategy.
Okay, so to let a machine execute that kind of long-term strategy,
Yeah.
you need a formal structure, a mathematical one.
Yep. And that structure is the framework we call the Markov decision process, or MDP.
The MDP.
Think of it as the formal contract. It's the rule book that dictates how the decision maker and its world are going to interact. Every single RL problem, whether it's robotics or a stock portfolio, it has to be framed in this contract.
And our source material lays out four essential parts for this. You have the agent,
The decision maker.
the environment, which is the context it's in, real or simulated. Then you have the action, which is the decision itself.
And then the crucial part, the reward.
Mm.
The single numeric signal that tells the agent if it did a good or a bad thing.
So it's a loop.
It's a continuous loop. The agent gets the current state, we call that $6, performs an action, a solar, and it gets back two things, a numeric reward, $2, and the next state, 60.
Yeah.
And that loop just keeps going.
I found a really key nuance here about the idea of state. It's not just a snapshot of the world, is it? The source makes a point to distinguish between the system's true state and the agent's observation.
Oh, that's critical, yeah. The system's true condition, the state, might have all this information the agent just can't see.
Right.
What the agent perceives is an occluded view, the observation. If the self-driving car is navigating, the true state includes the weather 50 miles away.
But the car can't see that.
It can't.
Yeah.
Its observation is just what its sensors show right now. And understanding the limitation is often key to how we design the agent's memory.
This brings us to what feels like the biggest headache in setting up an MDP, reward engineering. How do you take a fuzzy business goal like make users happier and turn it into a single number?
It's the ultimate problem. I mean, if that reward signal is too simple, the agent just optimizes for the wrong thing. We call it reward hacking.
Right.
The classic story here, which is, it's kind of funny, but it really highlights the danger, is the Swedish moose near Gothenburg back in 2011.
The famous drunken moose.
That's the one. So the moose's innate policy is just, maximize consumption to survive. It found all these fermented apples, an extremely high immediate sugar and alcohol reward.
A huge reward.
A huge one. And it optimized for that immediate reward perfectly. But he got stuck in a tree and nearly died. The short-term reward completely broke its long-term survival policy.
So if we pull that back to an industrial example, what's the fermented apple equivalent for, say, managing application containers?
Okay, so you might reward a container scaling agent for minimizing CPU usage. But if that reward is too powerful, the agent might just start shutting down necessary services.
Just to get the CPU metric down.
Exactly. It finds that local optimum of low CPU instead of the strategic one, which is low CPU while maintaining user latency. The policy is completely 100% dependent on that reward structure you build.
And since most of these tasks don't just end after one step, we need a way to measure success over the whole journey. Which brings us to the idea of the return.
Right. The return, which we label $, is the total reward you collect from this moment all the way to the end of the task. But what if the task is continuous, like a thermostat?
The return would just go to infinity.
It would. It's mathematically unmanageable. So to solve that, we introduce the discount factor.
The discount factor, or gamma. So conceptually, why is that so necessary?
It just exponentially reduces the value of future rewards. It's like it models our own preference for getting $100 today versus $100 in 10 years.
Okay, that makes sense.
If your discount factor is, say, 0.99, the agent is extremely patient. It cares a lot about rewards far in the future. If it's near zero, the agent is totally short-sighted. It only cares about right now. Setting that gamma is how we force strategic long-term thinking.
You know, this whole idea of valuing rewards differently over time, it's not something computer scientists just invented out of thin air. It has really deep roots in, well, in how we learn.
Absolutely. Reinforcement learning it's profoundly informed by early psychology and neuroscience. You look at Pavlovian conditioning.
The dogs and the bells.
Right. Linking an innate reflex to a totally new stimulus. That's the simplest form of this kind of associative learning.
But just associating two things doesn't get you to complex strategy. You need to be able to predict things.
And that's where the Rescorla-Wagner model came in, back in 1972. They formalized this idea of value estimation, and they showed that learning is driven primarily by surprise.
By surprise.
Yeah. The organism doesn't just react to a reward. It reacts the difference between what it expected to get and what it actually got. That difference is the prediction error.
And what's so fascinating is that this theoretical idea, this delta signal of prediction error, it actually has a physical counterpart in the human brain.
It does. Studies in the 90s confirmed that the neurotransmitter dopamine basically acts as the brain's delta. It doesn't signal pleasure or the reward itself.
It signals the error.
It signals the reward prediction error. If you expect $10 but you get 20, you get a big dopamine spike, and that drives learning. If you expect 10 and get 5, dopamine dips, and that drives correction. It's a signal for surprise, which is what directs our attention.
So the agent makes a prediction about its future, and when the actual reward comes in, that surprise signal, the delta, is what actually updates the model.
And this biological insight, it also informed how we structure modern algorithms. Researchers saw that the brain seems to have two systems. System 1, which is fast, instinctive.
And system 2, the slow, auditing, critical part.
Right. And that dual structure led directly to a whole family of algorithms called actor-critic.
Where the actor is the one making the split-second move.
The fast mover.
And the critic is the internal auditor, the one that's predicting the value of things and critiquing what the actor did.
Correct. The critic uses that delta, that prediction error signal, to train both itself and the actor at the same time. But before any of this can work, the agent has to figure out what's even possible. And that brings us to the core tension in all of RL.
The exploration versus exploitation trade-off.
Exactly. An agent has to balance trying new things, exploring unknown paths that might lead to huge rewards against just doing the best thing it already knows how to do.
Exploiting what it knows.
Right. And this is usually something you have to tune. If the agent explores too much, it wastes time. If it explores too little, it might get stuck in a decent but not great solution. And we often control this with a parameter, epsilon, that just dictates how often the agent should choose a random exploratory action.
Okay, so let's move from biology to the actual computation. We have our MDP defined. Now we need algorithms to solve it. Our source breaks this down into 3 historical pillars, showing how the algorithms evolved.
We can start with the earliest ones, which were purely sample-based, Monte Carlo methods, or MC.
Right, so MC samples its way to an answer. It learns from a full, complete experience. It's like learning a new board game by playing the entire game to the end.
Win or lose.
And only then, after it's all over, deciding what you might do differently next time.
And the key drawback is exactly that waiting period. MC has to run a full episode, the whole trajectory, before it can update its understanding of any single move. So it's slow to learn, but it can be useful for sampling big spaces.
Then the next pillar was dynamic programming, or DP. And this introduced a concept that just dramatically sped up learning.
Bootstrapping.
Bootstrapping.
So with bootstrapping, the algorithm doesn't wait for the final reward. It uses its own estimate of the future to update its current estimate. Think about it like using your GPS. Instead of driving the whole 500 miles to find out you were wrong, that's Monte Carlo, you trust the GPS's prediction for the next 5 minutes of traffic, and you update your total trip time immediately based on that.
That sounds way faster. So what's the catch?
The catch is that DP requires complete knowledge of the environment. You need a perfect map of the world, all the probabilities, and it's super computationally intensive because it has to visit every single state and action in that model.
So MC is data efficient but slow to update. DP is fast to update but needs this impossible perfect model. So what was the hybrid that changed everything?
Yeah, that was temporal difference learning,
Okay.
TD. This was the breakthrough. It keeps the sampling from MC so it learns from experience without a model, but it brings in the speed of DP's bootstrapping. It updates immediately after just one step using the difference between the reward it got and its own prediction. It's really the best of both worlds.
And TD learning is what brought us to two of the most foundational algorithms that are still used all the time, Q-learning and SARSA. Let's start with Q-learning. It's famously off policy. What does that actually mean for how the agent behaves?
Off policy means the agent is learning about the optimal path, no matter what it's actually doing to explore.
Okay, so it's like
Yes.
it's like your actual policy is, driving a slow, cautious minivan around. But Q-learning is simultaneously learning the optimal route and technique of an F1 race car driver.
So its update rule is always checking every possible action it could take in the next state. It doesn't argmax, and it picks the one with the highest future return to learn from. It's always thinking about the most aggressive optimal path.
Always. It always assumes that in the future it's going to act perfectly, which is why it finds those mathematically shortest paths. Now contrast that with SARSA, which is on policy.
On policy.
SARSA only learns about the value of the decisions it actually makes using its current, sometimes clumsy, exploratory policy. So SARSA is like a nervous new driver. It calculates its future return based on what it knows its current, possibly random self is going to do next. It learns the value of the path it's actually on.
Yes, it learns the value of the average expected return because it factors in those inevitable random mistakes from exploration. And this whole difference between the optimistic Q learner and the cautious SARSO learner is shown perfectly in the classic cliff walking problem.
Right, the cliff walking grid world. You get a huge negative reward for falling off the cliff, and the mathematically optimal path is the shortest one, which is right along the cliff edge.
Q-learning finds that optimal high-risk path. It wants to maximize the return, and that means taking the fewest steps if it succeeds.
But SARSA.
SARSA incorporates the randomness, those little epsilon greedy wobbles we talked about. It knows that those random kicks will happen, and if it's hugging the edge, they'll push it off the cliff. So SARSA learns the safe path, walking far away from the edge.
So in a real industrial setting, why would you ever pick Q-learning if it's designed to take these risks? Why not just default to the safer SARSA?
Because Q-learning tells you what the true maximum potential is. You might use Q-learning to find that theoretical ceiling for performance, and then use SARSA or some hybrid to find a practical, robust policy that can handle real-world noise. It depends entirely on your risk tolerance.
Which brings us to the industrial applications in the source material, like automatically scaling application containers. The old way is just simple rules, like if CPU hits 90%, add a server.
And that's a perfect sequential decision problem. That old thresholding, it leads to huge cost inefficiencies. You either have too many servers sitting idle, or you scramble too late when demand spikes.
So the RL agent learns the long-term cost of wasting resources versus the short-term cost of a little delay.
Exactly. And researchers found that using RL agents for this significantly improved cloud utilization. Major cost savings, all while keeping user latency stable.
And the choice of algorithm mattered there too.
It did. A model-based approach learned faster. But the way the model was built, it introduced this implicit bias. It preferred making servers bigger over just adding more servers. The takeaway is that success isn't just about the algorithm, it's about how you represent the problem and avoiding those hidden biases.
The source also mentioned real-time bidding for online ads. The state there was often defined by the average bid you could make with your remaining budget.
Yeah, in that case, RL finds a long-term strategy to get the most conversions within a fixed budget. It learns that, hey, early in the day when the budget is full, it can afford to make high bids.
But later on, it has to conserve.
Right. And crucially, the RL agent can adapt immediately if a new competitor enters the market and starts outbidding it. A traditional